Hi, my name is Thomas Hölzle, and today I want to show you how you can create your own operators in Tooll3. Tooll3 is a real-time animation software, open source, and originally coming from the demo scene, but also used for VJing. But it's growing constantly, and it has the potential to become the Blender of real-time, in my opinion. So it's really worth looking into it. And for me personally, the breakthrough came when I started to write my own shaders and create my own operators, because before I sometimes were missing things, or things were broken, or something didn't work like I wanted it to. And so beginning of this year, 2024, I finally decided, let's dive in. I will write my own shaders and extend Tooll in the areas where I need things different or more. Since it's open source, this is absolutely possible, and the awesome thing is that you can also create a pull request and integrate your creations into the main source, into the main tool, if you feel like that, if you want to share something with the community. So, without further ado, let's dive in. Okay, so what we are going to create is a radial force for the particle system in Tooll3. And we do that as an HLSL compute shader, which is the language for GPU programming that Tooll is using. Tooll is based on C#, so the Microsoft ecosystem, the net ecosystem. And Microsoft created HLSL for unknown reasons as an alternative to GLSL. It's very similar, but if you know GLSL, you will find some things are a bit different. Vector is called a float3 instead, and some other things, but it's only a handful of changes, so going between them is really easy. Tooll3 is mainly using C# for non-time critical things, and HLSL for everything where speed is of the essence, and this is mainly particles, points, and of course image shaders. Image shaders are done as pixel shaders, as you may be familiar with, and everything about points is using compute shaders. And this is what we will look into today. I think this is a very good introduction. If you never did any GPU shading, you should be still able to follow along nicely if you have some experience with coding and maybe saw some shader code before. But it's not super complicated, but I won't go into what variables are or stuff like that. I will mainly look into how Tooll3 works, how operators are created, how you can create your own, and how the whole system works, because there are some not so intuitive things. Overall, it's the most easy generation of shaders and operators I've ever used, and as soon as you did one or two, you will be quite familiar with the flow, and it's really simple. Okay, let's dive in. I created a very simple particle scene for this tutorial, and let's pin that here and start the playback so you can see. So I'm basically creating a radial points circle of points with 500 points, feed it into a particle system, so these points become the emitter of the particle system. I set it to 1 million points. This should be easy if you have a good graphics card. Set the initial velocity to 0, the emit mode for lines, drag to 0, and set W to particle age. W is a bit of a specialty in Tooll. You can think of it as a kind of weight or something. It is used to send out parameters to other nodes. So it's a free attribute, you could also say. And we want to have the particle age in that. Those particles, I set the initial velocity to 0. So these particles have no motion initially, but I connect a turbulence force, set a very low amount of influence, so it's very slow for the time being, and connect a time node to the phase input, so the noise is animated slowly and the particles get moved around over time differently by the noise. This goes into a spread point attribute, and this is a very nice node that uses, by default it uses the buffer order, but I usually use W again, and here in W we receive our particle age, and this is a value between 0 and 1. So we can here set the color of our particles to, over time, go from red, orange to, for instance, blue, and at the end fade out, so they don't end abruptly. From here we go into draw points. I have a very small point size. I don't use W for size because that I used, as you saw, for particle age. I use additive blend mode. I have the depth buffer writing disabled because additive looks only beautiful if you disable those. You lose the depth buffer, but your stuff looks like real additive and not some semi-additive like this. That's pretty ugly. So you have to live without a depth buffer. Then there's a camera in default settings, a render target, which basically is making this scene. Up until here it's still a 3D scene, and here it's getting rendered into an image. Also default settings, and as the last step I use tone mapping with the uncharted mode, which gives a very nice look to additive renders. Okay, so this is our little test scene. And now we want to look into creating an operator. And one thing that I can highly recommend is that you create operators from existing operators that already do something that is relatively close to what you're interested in to do. There also is the option to create operators here with create point compute shader or image effect shaders. The thing is that this point compute shader is actually for points like the radial points and not for particles. So the example doesn't contain any information how to deal with particles. So for particles I would highly recommend to go from existing forces, but otherwise these are also viable and it creates everything automatically for you with a nice example code in it. So that's even easier if you want to create something completely new, I would say. But if you want to have a particle force, start with a particle force, or if you have a certain image node that you like and that you would want to extend or improve or change completely, whatever you like, then I would usually go from an existing node. And this works like that. We start in this case with a directional force, which is the absolute minimum force anybody can create. It basically moves all particles along one direction, and this is a bit too much, so we lose all the particles, so let's reduce that. And they are going down because the direction pointer goes up, but the amount is negative, so it will go in the opposite direction of that. Okay, so now we want to create our own node, and this is very simple in Tooll. You can right click on the directional force node, go to simple definition and duplicate as new type. And this does a lot of things for you, but let's first concentrate on this dialog. First, you don't want to create your own stuff in the library. You can, but I would only recommend that if you want to contribute to Tooll, if you want to make forces or noises or shaders or whatever for a pull request, then you should put it in the fitting subdirectory. But usually, if you work on your own stuff, I would highly recommend that you go to user and then select your own namespace that you selected. Like when you first started Tooll, you got a dialog that asked you after your nickname or namespace name, and this is basically a directory in which you save your own work. It's still inside of the Tooll main application folder that has to do with how Tooll works. This will change in the future, but for now it's like that. So in my case, I use ScreenDream. That's my company's nickname. And we want to do a directional force, but I created several already to test out how this could work. And so I use a different name from the last time. And in here you can type a description if you want. Okay, hit duplicate. And now you have a one-to-one copy of the directional force node. So if I add it here, you will see that it does exactly the same thing the directional force did before. When we connected it, it falls down with the default values. And one thing that is a bit weird is that direction is now the second entry. That is probably a little bug. This should normally stay the same order than before. We will look into the interface later. And now you have a almost complete fresh copy of the code in the background, and that is very important to understand. In the background, Tooll creates a C# file and two interface files for you. So, and as you can see, I misspelled the name. I want to call it radial force, but too much going on and me being silly and me being on day 8 of my current fasting, so not as sharp as otherwise. Okay, but this is also interesting and good because you can actually rename your operators if something went wrong, and this works. You right click on your shader, your operator, go to symbol definition and rename symbol. So I renamed it radial force tutor and rename. Okay, so let's dive in. Okay, don't be scared. This looks like a lot, but it's actually pretty easy. Most of it you're not interested in at all. This down here below is only creating the gizmo that you can see if you enable this gizmo widget. And we won't look into that at all. You can check out all the operators that have such gizmos, but in this tutorial I won't go into that. It's basically very cool, but not my topic of today. So this, I move it a bit down and I move that a bit closer here. So only these are what interests us. And I want to go through them backwards. The first thing from the seen from the end is the output, and this is the particle output, and this is basically this thing where you can drag out a connection and connect it to the particle system. Oops. This is the connection to the whole render system, and this also is bidirectional, so through here the shader is also getting the particles. So this is a bit different from most other shaders where you have inputs on that side and they go through and come out over here, but particles only have one connection. You don't put points into them, but they get them from the particle system. So this is the output. Then we have a I'm using a Wacom tablet and I have to scale with my laptop, so that's a bit unfortunate. This is a node that basically just updates every frame, so has time changed. Then we have an execute node that only combines the gizmo stuff down below with with our actual particle work. And then here is the main central node that combines all the different stuff we need for a particle shader, for a compute shader. And this is basically that does all the work. And into that go different things. First and most important, there is a HLSL file that is actually a file on the hard drive. From this there is a thread size collected, which we will look into later when we look into the code. This is basically how the GPU should be used for parallel computation. Then we have the get particle components. That's basically a kind of a blind node which is getting all the particles from that output, which I mentioned before. And this also knows how many particles there are, and from the combination of the thread size and the particle count, this node computes how many dispatches there are, how many groups of those 64 threads are needed to compute all the particles. And finally, the particles themselves go in here. And you see that there's one more, and that is a buffer, a constant buffer. And this buffer, GPUs basically get everything as buffers. And this buffer is what's very interesting to us, because this is where the parameters in the user interface come in. If you click on the background here, you see the user interface of that node. And we have the amount, direction, random amount, and show gizmo. Show gizmo is a special input that allows you to select if you want to see the gizmo and when. And our main concern is now this buffer. And this is a buffer you can imagine as a kind of array, which is a very optimized format for GPUs. So, for instance, a texture is also a buffer, but a 2D buffer. If you think of it as an array, it would have 2 dimensions. And we mostly deal with floats here, so we have only floats to buffer. And this goes into the compute shader and allows the compute shader and our code to access the variables in the interface. And I will spend a bit of time here to explain that, because there are some caveats and some not so obvious things. First, the names you use here for the inputs, these are input nodes, are not important and not transported inside your shader, so only the order of those inputs, in the order they go in here, is important. And this allows you to deal with a problem or a specific thing that GPUs have, in that all variables are always used in batches of 4. So if you have a vector 3, you have to extract the components and feed it in here as floats. You can only put floats into this buffer. But HLSL is able, if those are one after the other, to create directly a vector 3 from it again. In HLSL, that would be float 3. And the caveat I spoke about is that those buffers can't, those vectors can't go over such a border. It's marked here with this little arrow. It always has to be put into a block of 4s completely. You can't have the last input over such a border. Otherwise, HLSL can't create one vector out of it automatically. If you have any problems in that direction, that may be the cause. So what we usually do is that we say, okay, we want to have the parameters in this order in the interface, but internally in the shader it doesn't matter at all in which order they come in, so we can juggle them around as we need it to fulfill that need of blocks of 4. So therefore we first have the vector 3 here and those 3 inputs, and only after that the amount is input and the random amount last, because those are floats, they are non-critical, but we will create another input, another vector, and for that we need to juggle around a bit with that, and I will do that next. And for the direction shader that we are currently still looking at, because it's still the same code and the same nodes as the original, there was no need for a center, because a direction is basically just a vector and doesn't have a center in that sense. But for our rotation it would be cool if we could define where the center of the rotation should be. So for that we create a new input, and this is right click again, add input parameter, and we will call that center. And this of course is not a float but a float 3. It's called here a vector 3, but in HLSL in the code it will be a float 3. So that's a bit different. You see it's ordered down there and numbered in a linear order, but this dialog stays open because we maybe want to create more inputs, and that's actually the case. The other thing I want to show you 2 different kinds of ways to treat velocity, particle velocity, and for that we will have a mode dropdown. So I create an input named mode, and dropdowns are always integers. It's basically, you can imagine it as each entry in the dropdown is numbered. The first is 0, the second is 1, but in the interface you later will see a dropdown, but internally it's just an integer value. And we add that. And that is not completely it. I also want to introduce a second input for the speed, because for that special kind of treatment with the velocity we need a separate speed. And that will be a float. So that this stays open is actually quite practical, as you can see, but now we have all of them and we can close that. Now I want to rearrange the order of things a bit. And for the way I want it to work, we want the direction on top, then the center, then the speed, then the random amount, then the amount, and then the mode. And finally the show gizmo. And now you can see that these numbers are no longer in order, and that our interface, if I click on the background, shows them out of order. This is in the new version that's already available in the developer and the GitHub developer branch. There's an editor where you can drag them around. In the old version, in the old standalone version, I'm currently using 3.9.2. This works a bit different, and that is a bit random, so I will at first ignore it and look into that only later. So I told you that those vectors need to be aligned in a special way here, but first we have to convert it to individual floats, and then you can see that our next block of 4 starts here. So I will connect them down here so that they will go under that. So now we have one parameter here, but the other inputs are nicely down there. Then I want the center to actually be over here, though it's a bit closer to the intended order. Now this moved around, but I can move that here. I want the random amount to be down there, and I want the mode there, but the mode is an integer, as you remember, and we can only deliver floats, so we have to convert that as well. And this would be an int to float. As you can see, the gizmo doesn't go in here, but it's only connected to those nodes that work for the gizmo stuff down there. So this is basically our input order. Now there's one specific caveat that's also a bit unfortunate. I want to actually rename direction to axis because we are rotating around an axis, and that's a bit clearer. And I want to rename the random amount to random speed. I can delete this input. You currently can't rename it. I can delete this input, simply hit delete and create a new input as a float, that is correct, and move it over here. And reconnect it there. That is one option. This is a good option if you're just creating your shader and are not worried about existing scenes, because those inputs are not known by their actual name, but they have internally a GUID number. And to have a quick look at that and how you can actually rename these things, I will go into the actual code for this. When we duplicated the node, Tooll3 actually created C# file and two interface files in the background and compiled it on the fly, so it's instantly working. You don't have to worry about that at all. If you have no problems in the code, this will just work. And let's look into that. I'm using Microsoft or Visual Studio Code for this. This is the actual C# code. It doesn't do much. The main work is done in the HLSL, but this is holding all the inputs, and you can see that every input and output has one of those super long random numbers, and they are globally unique identifiers, and they are so long and so complicated that the probability that somebody creates the same twice is so small that it's negligible. So now the thing is, if you have connections in an existing project and you delete an input and create it anew, it gets a new GUID. And the connections will no longer recognize this input, so your old projects will basically be broken. The other option for that is that you go into this CS file and rename it here. And I want my direction to be called axis. And as soon as I save it, you see it's still called direction, but when I save it, it's instantly axis. So this is super simple, instant. The shader is recompiled. Don't be afraid of all this complexity. Basically, it's just, this is a vector3 input and called axis, and the other stuff is usually created automatically. Also, those interface files that define where the things are also created automatically. Okay, so we have renamed that. And the other thing that we have to look into is dropdowns. Because if you check here, our mode is currently an integer, and we don't really want that. We want it to be a dropdown. And this can't currently be done in the Tooll interface. That is the other thing that we need to go into that code. And basically what we are doing is that we look into another shader that is using dropdowns and copy some code from that. So we go to the library. This is the operator. This is the Tooll directory. There we have the operators. And in user screen dream, there are my own shaders, and in library there are the factory things, and I want to go to point particles, and you can see the particle system is right here. And if we look into all these things, it's the same structure than our own code, and then there is one line that's a bit different, and you can see that here there is a MappedType, set modes, and here there is an enumeration, set modes with the entries of the menu. And the code we need is that, and then we go to our own shader, and we have our mode here. It's still, the order is still wrong, but let's put this here. And we don't want it to be called set modes, but just modes. And now we can enter the names of our drop-down entries here, and the first will be additive, and the other will be proportional. Okay. And when we save that, we can see that now we have a proper drop down here with 2 entries that we entered. So that is a bit on the nerdy side. That is not yet as slick and nice as many other things in Tooll, but it's not so bad either. So you should survive the experience, I think. Basically, look at another node that has this kind of drop down in it, and just copy that last part of the line, that it's this input is a mapped type, which then needs an enumeration of the same name as that's given here, the type of name. Okay, so we have a slightly unordered interface, but we have all our settings. Another thing that is interesting here is that you can create your own defaults. So we later want a default of 1. And you can right click here and set as default an amount of 0.5, which we can also set as default. We want additive as our default value, and random speed at 0 is already what we want. Okay, this was a lot of stuff already here with nodes and very theoretical because we don't see any code yet. So one very important thing is what we will do now, and this is that by creating this node automatically, Tooll took care of all these GUIDs and all these nodes and duplicated them without any interference with the existing node. The only thing that it just copies is actually this HLSL code. So we have to take care of that next. So this is where the HLSL stuff comes from, and to edit that you can click on edit here, and then it will be opened in your code editor. Like I said, for me it's Visual Studio Code, but you can use whatever you want. And now we want to rename that to make it unique. Save as, and now you can see that currently I'm still in the particles folder here, and it was originally the directional force, but we want to have it in our own folder, and for that you can directly click here on resources to jump to folders up and go to user, and in my case Screen Dream. You should go to your own folder, and you see there are my previous trials, and this time I will try to type this correctly. Force, and let's call this Tuto. The name is basically whatever you want. It just has to be unique so that it doesn't interfere with other stuff. This is also true for the operators themselves because they are globally available. You currently in this version you can't have operators with the same name twice, even in your own namespace. The next version will deal with that, but that's not ready yet. the so-called main branch will change a lot of things to the better. Okay, I save that. And now we are working in this custom version of it, but our force is still using the same name. So we have to click here to assign our new custom force to our shader. Again, resources, users, screen dream, and radial force tuto. And now we are really independent from the original directional force, and the radial force is now, the radial force tuto is now non-connected to any other nodes. Okay, and now let's finally dive into the code. I will first give you a slide overview what this stuff does. It's basically the same as in other compute shader systems, but if you know some C or C++ or GLSL or anything, it should be quite familiar. It's not so different from other shading languages or programming languages. At first, there are includes. That is basically, there are in the library some HLSL files that include functions that we want to use, and they are just integrated into that file by using this include and the path to them. And the first is a function library for random numbers. The second is a noise function library, and since this isn't used, that is probably a leftover from something else, we can comment that out. Then we have a link to the point HLL. This is where our point values are defined, our members of the point enumeration. And then finally there are quad functions, which are also not used in this thing. So I will put that out as well. These are quaternion rotation functions. And then we see a list of parameters, and these basically are our incoming parameters, and we now have to change them. And this comes in as a constant buffer, and this buffer is registered as B0, and you can see that here there's a float3 direction, and this is what I told you before, that HLSL is able to combine these three floats back into a float3, a vector, automatically if they don't reach over such a border of those blocks of 4. So this is how this works. And since I changed the name in the interface, I want to change it here as well. So this should be axis, which of course leads to that our code down here has an error. And we start with axis, that is correct. But then there is speed, this is new. Then we have our next vector, which is also new, so I have to enter that as well. Float3 center. Then as the next input in line we have random speed, so I can simply drag that up and rename it to random speed. And change it here as well. And then we have amount and mode. Awesome. Mode was already in here because that also seems to be a leftover from earlier incarnations of this node. So that was lucky that we have that already, and it comes in as a float as well. So we have our parameters. Next, HLSL creates a read-write structured buffer for our particles. And it's called particles and has the assignation U0. But one thing I want to look into quickly is this particle thing, because that will become important later. And I told you that this point HLSL file is important for us, and I will open that now. So let's look for it on the hard disk. The HLSL files are in resources, and this is in library shared. So you see there's our point HLSL. I will close that down. And you can see that there are two structs defined here. One for points, one for particles. And each point in Tooll3 has all those attributes. So the first is a vector and holds the position. The second is this W attribute. Then comes rotation, that is the orientation of the point. All points have an orientation in Tooll, which, if you imagine you want to instantiate, for instance, a cube on the point, you may want that cube to have a certain orientation, and that would be defined by the point's rotation. Then we have a color. Stretch is currently what I would call scale, and then finally selected, that is a newer attribute which you can use to save selections on the points. Okay, that's the point, but we are dealing with particles, and particles are different because they need a bit of a different feature set. And the first is position, of course, it has to be somewhere, but the second is radius. So that's basically, if you have a point particle, that would be its radius. Then rotation, that's the same. Then a color, that's also the same, but then we have velocity, that is the direction and the speed, so to say, in which the particle is moving. The speed is encoded in the length of the vector, if you're familiar with that. And finally, the birth time. You saw that I have the H active in the particle system to be written into W, and each particle saves when it's born. So from that, the particle system can compute how old it is. Okay, so these are the attributes we have available. And if we look at our radial force again, then you can maybe now understand that this structure buffer is of the kind particle. Okay. The next thing is a bit complicated, and I will only slightly touch onto it, and this is numthreads. This is basically the number of threads your GPU should use to compute all these points. And in our case, those particles are basically linearly numbered from 0 to 1 million. And so this is a one-dimensional thread declaration. You can also have 2- and 3-dimensional declarations. 2-dimensional, you could imagine, is very good for textures because they have X and Y, and that is internally in the GPU better optimized if you have them like 8 times 8, 8, 8. And you could also work with 3-dimensional textures and use a full 3-dimensional numthreads declaration. Then finally, our code starts. Main is something, I don't know if you have seen it before when we had this active. There's an entry point in that shader code, and that is main here. And this is what this means. So the shader is basically told where to start. Where is the stuff I should do? Because you can have additional functions in here, as many as you want, and it's important to tell the system what is my actually code that I should run. And this is in this case main. It's a void because it doesn't turn anything. Instead, it directly writes into those particles. It's a read and write buffer, so it doesn't return a new buffer, but it writes directly into the existing buffer. That's a bit specific. With points, it's usually that you have a static buffer, an input buffer, and a specific output buffer. So things are copied in memory, and this is actually working on the existing particles. So void, giving nothing back, main, and then it's an unsigned integer 3, I. And this is basically our counter variable. it's a vector integer unsigned. The numbers of our particles are only positive. We don't have particle -5 or something. And they are 3 because there are 3 possible dimensions here. We only use 1, so we will only ever deal with I.x, like you can see it down there, which is the way to address the first entry in that counter, which it basically is. And this is the another hardwired thing for the thread ID stuff. And then our actually function starts, and it starts with even more boilerplate stuff that has nothing to do with our actual force. At first, here are 2 variables created, also unsigned integers. The first is called maxParticleCount, and the second is called underscore, and I hate that. So I will call that stride. And also replace that name. The idea behind this underscore is that it's not used in our shader, but I don't find it intuitive to have underscore as a variable, so I instantly change that when I see it. And these 2 variables are empty, and they are only used to be fed into this function. I don't know if you're familiar with functions that directly write into variables, but this is what happens here. So we are using our particles buffer, and with the dot notation, HLSL also uses the dot notation like pretty much every other language out there, or most of them at least. And then we invoke a function called getDimensions to find out basically how many particles there are in our buffer. And for that, this function, it doesn't return a value, but it uses these 2 variables to write into. And after that function, inside of those variables, you have the actual particle count and the stride. And the next line is also boilerplate. If I.x, that is our counter of the current particle we are working off. So this function is basically evoked for every particle. So, and in this counter variable, we have the number of the current particle we are working on. So I.x gives us the current particle number. And if that is bigger or equal to maxParticleCount, which we retrieved here, which is the overall particle count, within our case was 1 million, then it should return, which basically means stop the whole thing and go home. This is to make sure that no problems arise later on if we use those counters. So if it's outside of the scope of our buffer, then it should simply stop doing anything. So this was all the boilerplate, and now comes our outrageous complicated actual code. You remember it was a directional force. So how that works is that we compute how far should our particle travel for this frame. And this is saved in a float3 because it also has a direction. It is a directional vector with a length, and it's called offset, and it is fed from this side with axis, which was in the original thing direction, if you remember that. And this is this was 0, 1, 0, so a vector with a length of 1 multiplied by amount. So maybe you remember it was 0.007 negative. So this will be scaled small. Then this random hash will be added. So as you saw, these hash functions are connected and included in this shader. So this basically generates a random number with one input. And the input is our current particle number. So our counter gives us the particle number we are working on, and this should be the random number should be different for every particle. So we are feeding in the particle number here. Multiply that with random speed, which is our interface value that we have to define how much of this random stuff we want on each particle, and this is added to 1. So if this is 0, this whole thing will equate to 0, and so this thing will then be multiplied by 1. So it will be actually the same value that it was before. If random speed is set to anything, this will be bigger than 0, and will be multiplied with this random number, which is a value between 0 and 1. So this will then become effective and scale this up with the computed random value. Okay, and this is how much our particle should travel, and this is then simply added to particles, our current particle number. This bracket notation you're probably familiar with. This is how we access an array. Our particles are an array, and this is our current particle, and it has the velocity as an parameter. And as you remember, our points have a velocity in their particle structure. So this is simply set to plus equals offset, means that this will be added to this directly. If you want to write it differently, you could remove the plus and say particles I.x velocity equals particles I.x velocity plus offset. That's a bit tedious, and because that's used so often and needed so often, there's this shortcut which will simply add that on that side to that. This also works with multiplication and division and subtraction and stuff. Okay, so this is how the current shader works. Now we want to change this shader into a rotational force, into a radial rotational force. And I will move the code editor over so that we can see what happens over there, although there won't happen anything yet. Every time you save your code, it is instantly updated, which makes Tooll a really good tool to develop shaders, because it's so instant. You just type something, hit save, and we'll instantly see if it's working. You see that here it's updated resources, users, grain dream, radial force 2 to HLSL, and if there's an error, it will be red and show you some feedback. But we only changed stuff that now actually is correct and change it everywhere. So this is basically still the same shader as before. And now I want to implement our new code, and this will first be about retrieving the position of our points. So in this directional force, it didn't matter where the point originally was. There was just a value added to the velocity so that the point would move in the direction with the speed of that velocity vector. But we care about where our points are, so we first need to load them. Okay, so I create a float3. I call it pos, and this should equal normalize. We need to normalize that. Okay, and we need brackets I.x dot position. As you can see, we now access the position of our particles, and we want to subtract the center of that. Okay, so let's break down that for you. Normalizing means that we make basically a direction out of our position. If you imagine our axis, currently by default it points into the z-axis away from us, or along our view axis when we look at the screen. And every point is somewhere around that. Now we want to know where it is, but only the direction, because we want to compute our rotation from that. We are not interested how far away it is in the implementation I'm doing, but only in where it is, so we can compute where it should go next. So if it's up here and it should rotate, it should go over there. If it's down there, it should be over there. And normalizing makes a vector the length 1. So it's very simple. If you have a vector like this is 0, 1, 0, so the length of that is actually 1. For diagonal and more complex vectors, this is not quite as easy. Normalize internally does Pythagoras, as you may remember, and the hypotenuse is basically our length of that vector. If you remember your vector math, like x, y, and this would be your actual length of that vector. And I subtract the center position, which is our where it should rotate around, from the position, and this will simply make it rotate around that. The next we need is our actual axis. And again, we will normalize it, because the user for the axis can enter all kinds of stuff here, and we want to make sure that it has a length of 1. That becomes important later. Okay, and here we only use our input value, that one. And this is now also normalized. And now we make the position vector, which so far still points somewhere into space, perpendicular to our axis. That works like that. Pos equals pos minus dot product ax pos times ax, making one vector perpendicular to another so that they form the basis of a coordinate system, you could say. What we have now is one vector that points along our viewing axis, we have our axis, and if I said that, oh, it's actually wrong, the default, I want it like that. Set as default. Okay, it's pointing along our view axis, and you can already see that it's now going outward from that. We now have the axis around we want to rotate, and we have modified our position so that this vector pos is now pointing 90 degrees away from that axis. And from that, we can now create our direction in which we want to move, which would be the tangent of that vector pointing outwards. And so I will call that 3 deer for actual direction we want to travel in. And there is this function that's called a crossproduct, and we put in our 2 perpendicular vectors, and this will give us the third direction to form a complete 3-dimensional coordinate system. We had one pointing away from us into the depth of the screen, then we have one pointing outward in the direction of the point. Let's say we use a point here, and this cross product will now give us a vector that points in this direction or in this direction, depending on the order of those two. Oh, sorry, this is missing an I. And if you think about it, if our point is here and we have this direction perpendicular to it, then this will be actually our tangent direction, which is what we want. We want each point to move in the tangent direction to make it rotate. So we now have that, and that is almost all we need. This is the main computation we do. Now we have to create some stuff so we can scale things and define our speed. So we will create another float 3, and I call that vel, because that will be now our what we add to the velocity later on. And for this we want our direction we have computed, the actual tangent movement. We want to multiply that with speed from our interface, and we want to multiply that with exactly the same that was used down here. So I will actually copy and paste that. So our rotation will be able to have slight random speeds if we want the particles to be more diffuse and not so regular. So this is basically the computation of our actual value that we now want to add to our velocity. Now, as you can see, this is almost the same as that line, and so I can delete that one. And I will basically, well, but we have that drop down, remember? And for that drop down to work, we get a 0 or a 1, and it should behave one way or the other. And I enjoy using switch. Many people prefer if. I originally learned programming first with Visual Basic, but then with C, and in C, switch was always the fastest. And we now want to switch over our mode input. Remember, our interface value is an integer called mode, and we get a 0 or a 1, but we had to convert it to float for the buffer, and with putting int in front of it, it makes it an integer again. So switch only works with integers. Okay, and then we need curly brackets. If you're familiar with switch, you know that there now comes a case. We now define the two cases we need, and that is very simple. The first version we want is actually this. This is the additive thing I talked about. And in this case, our computed value will simply be added to the velocity. But I want to scale it a bit. And that is simply, if you ever heard the name magic numbers, this is such a magic number because then the interface values are nicer. It's sometimes annoying if you have to enter 0.005 or something, and it's much nicer to have something around 1. On one hand, we want to multiply it with amount and then multiply it again with 0.1. This just makes the values nicer. Amount is in this additive mode just there to balance it out with the other mode. It doesn't have much of a meaning here. I just balanced everything out that it works nicely for both of those modes. Mainly our speed is already set here, but for the second mode, amount has a different meaning than here. Here it's basically another layer of speed added to it. And then the important thing is that you now put a break here. For this second implementation, I want to show you slightly different. Particles I.x dot velocity equals, and what we do now is that we lerp between two values. Lerp is linear interpolation, and it's a function that's available almost everywhere. And this allows you to enter two values and interpolate between them. And the one value we want to interpolate between is the existing velocity of the particle. The particle already has some velocity if it's moving, and we want to interpolate between that existing velocity and our computed new velocity. The third parameter of lerp is the interpolation amount. So basically what we put in here, if that is 0, it will use particles velocity as it is. If it's 1, it will use velocity as we compute it is, and interpolate linearly between these. Okay, so and we want to have amount, and again times 0.1. Again, this is a magic number that I found by trial and error that makes the parameters behave nicely and the ranges be pretty usable. Okay, so I save now, and I made an error. You see that there's a it couldn't update the shader. The slightly sad thing is that the console doesn't give you any more information. By the way, if you're doing a lot of coding, you may want to have the console in here, then you can switch to it and see it, because here if you accidentally click on it, this on-the-fly console is emptied, and here it stays always. So I usually in my layout I have this behind the output. So what did we do wrong? It's hard to say, but help is close. So we have this where our actual shader is. You can see if we hover over that, we can see that in line 40 there is a non-empty case statement, must have break or return. Oh, okay, so let's see what I did wrong there. Oh yes, you see HLSL doesn't let you forget the break. In C you were allowed to forget it, and that was painful to find. And now it actually works. Awesome. So we now have a shader that does rotation, but we don't see it yet. But this is basically our code. So, okay, now let's look into using this stuff. And let's once again try if this does anything. For me, it only works on full moons and Thursdays, and there need some toads to be buried somewhere. I don't know. I can highly recommend to go for the dev version, the dev branch, and compile Tooll yourself. Then you will have a lot of much more current updates, and one of the nicest of them is the new interface editor. That is really cool, and that makes it super easy because you can drag and drop your parameters around and make the settings in a much nicer way. Thomas Mann did a very great job on that. Okay, so now we have a radial force, but we don't see that much. Let's see. So we are in additive mode and our particles are flying away. But I guess that I had this turbulence force very low, so let's add some more turbulence. And you can see that something is rotating. It's still a bit very... Let's try that a bit stronger. Oops. Okay, so now our rotation could be a bit stronger so that we get more of an impression of it actually rotating. Maybe we can make this a bit more obvious. I will zoom out here a bit. And for this, let's focus that one so it looks a bit garish, but it's better visible. The thing is that with this additive mode, each particle keeps its current velocity and the new tangent is added to it. So particles always fly basically a bit outwards because they were going in that direction, and then you add a bit of going in that direction to it. But so it's pretty realistic actually, because you have this centrifugal force going on. But I found it also a bit not so cool that it's basically always shooting to the outside. You can counteract that with other forces, but this is why I implemented the other mode here. The additive you can use when you want your particles to rotate, but also fly away. And this will do this quite heavily. Okay, and when we use the proportional mode, then you can see that they stay much more... Oh, we have to reduce the turbulence. I made that pretty big. Let's reset this shortly. And now you can see that the particles don't fly so much to the outside, but mostly stay where they are on the radius side and just rotate, and that is very nice to have as an option. And this is what the proportional mode does. And to explain that maybe a bit, we blend between the existing, as you may remember, we interpolate between our existing velocity, the speed and direction the particles move in when they come into that code, and the new velocity we are computing. And the amount defines how strong our newly computed velocity should be, and reduces the existing velocity at the same time. So if this would be 0.5, it would be half of the particle velocity and half of our new computed value. The good thing about that is that it basically keeps our stuff, it rotates our stuff, and prevents that we constantly add velocity on top of each other. The not so good thing about it is that it overrides partly the forces that come before. So in some situations you may sometimes have to increase your turbulence if you increase the amount. So if I increase that, remember I multiplied it by 0.1, so it will fully lerp at 10 actually, but the usual area, the useful area, is between, let's say, 0 and 0.1, and because I multiplied that by 0.1, it's now between 0 and 1, which is much nicer to work with. So if this would be 10, if we reset, it looks like nothing is happening, but it now only rotates. The turbulence has more or less almost no influence, and the directional force moves them slightly in our direction. But now the newly computed velocity is almost completely overriding our existing velocity. Existing also A, where they were flying before, and B, the other forces. So 10 is definitely not what you want. In many cases, something like 0.5, which would be 0.05 without the multiplication, the internal one, gives really nice results. And yeah, that is most of what I want to show you today. One thing that I just saw is that this was by default doing very small changes, and this is also interesting. If you go here to parameter settings, you can influence the default scale of the change of the parameter. So 0.001 is very small, so I like 0.1. You can also set a lower and upper limit. So for this value, it makes sense to mostly work between 0 and, yeah, in theory 10. You can get out of that range. The lerp, the linear interpolation, also works outside of that. But this makes the interface show what the optimal range is, we could say. You can also clamp that, then it's not possible to go outside of the range inside of the interface with the sliders, but I don't want to do that. Okay, so now we have most of our work done. We could do that for the other values as well, but these can be positive or negative in as big as the user wants. Oh, I didn't show you the center, so we can move that into the negative area, and now all the particles rotate around something over here. More obvious if we start anew. So now our center is, I don't know, somewhere here. And you can move that wherever you want. speed I talked about, this is independent from amount. So amount is how much you override it. And I found that just the amount is then too little to actually define how fast it should rotate. So you have now a separate option to actually rotate. And if you don't want them to fly out, you can make that bigger. Then they will stay closer, because then more lerp, more of the new computed thing is used, but you again lose more of the turbulence force. In that case, you would have to raise the amount of that quite a lot. There are 3 more things I want to go into. And the first is how you create the documentation. You can see when we originally created that force, I put that comment in there, and you can go into read more and click on that text, and then you can actually write in here some documentation, like particle force that rotates particles around a center with center. Normally you would now also write some documentation for the parameters, what they mean, and you can also link to examples or other nodes that are interesting in that context. I won't do that now, but I want to encourage you to look at other shaders that have also examples. I will tell you about examples shortly. And you can then see how you can use words in brackets in here to link to other related stuff. I won't do that now. That video is getting too long otherwise. If I close that, then you can see that this is now visible here. And if I close the help, this is now down there. And you can, I would encourage you to go much more extensive than that. The other thing you can do is that, for instance, this mode, we want to have a bit of a explanation about that. And if you go into that parameter edit settings, parameter settings for that mode, you can write documentation for that node. And I only write a quick example. Okay, so I type something in quickly and will cut out the typing. So just you see, so you can add this kind of documentation in here. And if you now go over mode, you get a tooltip with that documentation in it. There's no real advanced options to make that pretty, but it works pretty good. One other thing is, if you want to create an example for an operator, that example has to have exactly the same name, but with example behind it without any empty space. So it would be radial force underscore tutor example with a big E. If that exists, then the system will know that, and as you may have seen before, let's open the symbol library and look at points and particles, and you can see, no, they don't have here's an example. So this example, if I drag it in, it's called collision force, the force, and the collision force example is basically collision force example, and this name then will be found and automatically shown here. You can therefore only have one example in this way, but you can have multiple of them with the brackets thing. Checked through some notes. I don't have an example prepared, sadly. Sorry for that. And the last thing I want to talk about is something I personally use too little. Thomas Mann always says I should use it more. And this is the presets. You can have presets for your operators, and they are very easy to create. You can name them. them some name you find useful, and you then can step between them. So let's give this some crazy speed, maybe very fast, and but more amount so that it stays pretty circular and centered around something else. So, and go to variations and have another preset here, and call it spiral maybe. And now you can switch between those by clicking on them. And the most interesting thing is you can hold Alt and fade them in and out, and basically go fluidly between them. So this is 100% that one, and that is 100% the other one. It's quite nice, and you can test them out by just rolling over the thumbnails and see what they are actually doing. Okay, those last points, the documentation, the presets and the example, are especially important if you want to contribute, because other users will not know what your stuff is doing, and they need documentation, they love presets, and are very much happy to see an example of what your node actually does. I used this very simple example in here because you may have seen it on YouTube or Instagram. I posted a rather interesting result I had when I first tried it out, but that was so hectical to have here for the explanation that I decided not to use it as a default example scene. But if you're interested in that, let me know, and I can at one point show you how I did that. And with that, let me make that bigger and Control P, put that in the background. And with that, this is also using the rotational force in combination with other forces, with the volume force, and I think there was one other, and shows you that you can combine rotation and rotational things in very interesting ways with every other force. So I hope that you have learned something, that you enjoyed this. This is my first video tutorial. I plan to do more. I don't know why it's my first. I do 3D for 30 years and somehow it never happened. It's sometimes like that, and I actually love teaching. I love to show stuff, and I hope I will do that more in the future. So if you're interested in specific topics, let me know, and yeah, enjoy your radial force. And if there's anything unclear, or if I missed something which may have happened, write it in the comments. I'm happy to help you out and clear up things if something's not understandable. Have a nice day. Thanks for watching and listening, and all the best. Tooll away!